Assalamu alaikum wa rahmatullahi wa barakatuh. This is the third part of chapter 4, which is a supplement for part 2. At the end of this part, you are going to be able to establish the differential equation which governs the simple harmonic motion of a horizontal elastic pendulum using methods in physics. Before we start, remember what we have taken in the previous videos. When we ask about the nature of motion, the answer could be simple harmonic motion, uniform rectilinear motion, uniformly accelerated rectilinear motion, etc. So simple harmonic motion is an answer of the question about the nature of motion. Also, when we ask about the nature of oscillation, the answer is either free undamped mechanical oscillation, free damped mechanical oscillation, driven oscillation, or forced oscillation. Here we are talking about free undamped mechanical oscillation. Remember, we have taken before about simple harmonic motion, and we said that it is defined if the differential equation is of the form x double prime plus omega 0 squared x equals to 0 and x equals to a cosine omega 0 t plus phi or a sine omega 0 t plus phi. For a free undamped mechanical oscillation, we said that mechanical energy is conserved and there is no non-conservative forces. To study the characteristics of free undamped mechanical oscillation in physics, we consider a horizontal elastic pendulum formed of a solid of mass m and a spring of stiffness k of negligible mass and non-joined turns. The solid is attached to one end of the spring and whose other end is attached to a fixed support. X prime or x is a horizontal axis positively oriented to the right. When the spring is neither elongated nor compressed, the abscissa of Chi is x equals to 0, which is called the equilibrium position. To start the study of the oscillation, the solid is moved a distance x equals to a and then released. The maximum displacement from equilibrium point is called amplitude. The oscillator then is in simple harmonic motion. Actually, we have two methods to find the differential equation. Method 1. Consider the following horizontal elastic pendulum where the horizontal plane passing through the center of mass G is taken as reference of gravitational potential energy. Then the height of G is 0, and x is the elongation of the spring at an instant t. We are going to benefit from the conservation of the mechanical energy. So one must write the expression of the mechanical energy at any time when the abscissa x and the velocity v are not 0. Avoid the two extreme positions and the equilibrium position in your study. Then the mechanical energy is the kinetic plus gravitational potential energy plus the elastic potential energy. But we have said that the gravitational potential energy is 0, then the mechanical energy is written as half mv squared plus half k x squared. As the oscillations are made without any non-conservative forces, then the mechanical energy of the system is conserved. Do you have any idea how this may help us to find the differential equation? I will give you a hint. We need to make derivative to get to the differential equation. So, it's right. We can make derivative for the mechanical energy and its expression, which will be equal to 0 since mechanical energy is constant. Then, to make derivative, we should remember some rules of derivatives, especially the derivative of x squared, which is 2xv, and that of v, which is 2va, since x and v are functions of time. Following the rules, we find that this equation becomes 0 equals to half m 2v x double prime plus half k 2x v. Take v common, then we have 0 equals to v into mx double prime plus kx. This means in math that v equals to 0 or mx double prime plus kx equals to 0 at any time. And v equals to 0 at any time means that there is no motion at all. And that is not the case that we studied. So the one solution of this equation is mx double prime plus kx equals to 0. This equation then can be written as x double prime plus k over mx equals to 0. This differential equation is of second order and of the form x double prime plus omega 0 squared x equals to 0, where by comparison it shows that omega 0 squared equals to k over m. This method should be studied very well. What is the other method? It is Newton's second law. This law deals with the study of the effect of the force on the system. So we should first define the system. Consider the same oscillator defined before. The system to be studied is solid M. What are the forces acting on it? Its weight, the normal reaction of support, and the tension of the spring. The tension of the spring T vector is always of an expression T vector equals to minus kx I vector, and its algebraic value is T equals to minus kx. Since it is a restoring force, it is opposite to the displacement of the spring. Then, according to Newton's second law, the sum of forces external acting on the solid equals to ma vector. Then, it is written as mg vector plus n vector plus t vector equals to ma vector. By projecting along x prime or x, we can get to the answer kx plus mx double prime equals to 0. Then x double prime plus k over mx equals to 0, and this is also the second order differential equation. Please pause the video and repeat the two methods by yourselves on your copybook. Now, what is the physical meaning of each factor of the time equation? Take x equals to a sine omega 0 t plus phi. X is the abscissa of G, the center of mass. The absolute value of A is xm, the maximum displacement, which is all the time positive. Omega 0, which is radical k over m, and it's all the time positive, it is the proper angular frequency. Phi, it is the phase at t equals to 0, and finally omega 0 t plus phi is the phase at an instant t. What is the unit? The unit of x is meter. The amplitude also, it's meter. Omega 0 is radians per second, phi, and omega 0 t plus phi in radians. It's important to know that x lies between minus xm and xm. xa and xm have the same unit. The amplitude depends on x0 and v0. Besides, omega 0 depends only on the characteristics m and k of the oscillator, while finally phi depends on x0 and v0, the initial values. In addition to their meanings, we should understand more how they affect the motion. So suppose we have a time equation like x equals to 1 times sine 2 pi t. The amplitude is 1 centimeter. Omega 0 is 2 pi radians per second. And following the expression t0 equals to 2 pi over omega 0, the period is 1 second. The phase here is just 0. What is the graph of this equation? Okay, it is a sinusoidal one. We can see that it has a constant amplitude, which is 1, as we said, and it starts from 0 as phase is 0 at t equals to 0. Its period is only 1 second. If x equals to 1.5 sine 2 pi t, let's find its characteristics. The amplitude then is 1.5 centimeters, omega 0 is 2 pi, now period is 1 second, it's still 1 second, and the phase is also 0. So the only factor that is varied is its amplitude. It shows us that its amplitude increased by half, but all other characteristics are just the same. What if x equals to 1 sine pi t? The amplitude here is 1 centimeter as the origin one. Omega 0 is pi. Period is 2 seconds. The phase is still 0. So what is the difference between them? We can find that in this case, the amplitude is still the same, the initial value is still the same, but instead of having period 1 second, it's 2 seconds, and here the period on the graph becomes wider, since the period is doubled while the angular frequency becomes half of it. Remember that what changes the angular frequency is the change in the stiffness or the mass, since omega 0 equals to radical k over m. Finally, consider the expression x equals to 1 sine 2 pi t plus pi over 4. Here, what do you think? What about the amplitude? Yes, it's 1 centimeter. What about the angular frequency? Okay, it's 2 pi radians per second. So, the period is 1 second. Now, what is the phase at t equals to 0? It is pi over 4. Let's draw it. It seems that the oscillation leads the first one by pi over 4. We have a little shift in the graph, and it seems that phi affects in the initial start of the oscillation. The time equation then for simple harmonic motion can be written as x equals to xm sine omega 0 t plus phi, where its characteristics to be studied by heart, expressions and names as proper angular frequency omega 0 is radical k over m. Proper period t 0 is 2 pi over omega 0, which is 2 pi radical m over k. Proper frequency, which is 1 over the proper period, and then it is 1 over 2 pi radical k over m, the amplitude xm, and note that omega 0, f0, and t0 are called oscillator characteristics since they depend only on the characteristics k and m of the oscillator. After defining the time equation, we can now define the velocity and acceleration time equations by the derivative of x and the derivative of v, or the second derivative of x. The amplitude of x is xm, that of v is xm omega 0, and that of the acceleration is omega 0 squared xm. It is always positive. Then v can be written as v maximum sine omega 0 t plus phi plus pi over 2, since cosine alpha equals to sine alpha plus pi over 2. The acceleration a equals to minus omega 0 squared x, and can be written as a maximum sine omega 0 t plus phi plus pi, since minus sine alpha equals to sine alpha plus pi, and this is used if I want to convert from cosine to sine and vice versa. At last, we have all these ideas that mentioned before, and we add to it the proper angular frequency and the proper period. This is the end of part 3. study well, and thanks for watching.